The universe is vast, mysterious, and full of questions that fascinate scientists and enthusiasts alike. One of the most exciting areas in modern physics is the search for new fundamental forces, beyond the four we know: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. For decades, researchers have wondered if there could be additional forces that operate on scales we don't yet understand. Some scientists suggest a fifth force might exist, possibly connected to dark matter or dark energy, which could explain the universe's accelerating expansion. To find these forces, scientists study high-energy particles and cosmic phenomena, hoping to unlock new secrets of reality. Scientists study particle collisions at places like the Large Hadron Collider, where particles smash together at high speeds, recreating conditions just after the Big Bang. These experiments may reveal new particles or forces beyond the known four fundamental forces: gravity, electromagnetism, strong nuclear, and weak nuclear forces. But discovering new forces could help explain mysterious gravitational effects seen in galaxy rotations, or even unify general relativity with quantum mechanics, transforming our understanding of the universe. Symmetry in nature also plays a key role in these forces, and exploring it might unlock new interactions. String theory suggests extra dimensions beyond our familiar three, which could harbor unique forces affecting the cosmos. Some theories even propose that time itself may be influenced by unknown forces, challenging our ideas of reality and causality. Throughout history, humanity's curiosity about the cosmos has driven scientific progress. From ancient civilizations using stars for navigation to the Greek philosophers proposing early models of the universe, the Middle Ages preserved and expanded this knowledge, leading to the Renaissance. The heliocentric model introduced by Copernicus, refined by Kepler's planetary laws and Newton's gravity, revolutionized astronomy. The invention of the telescope allowed direct observations, supporting these ideas. In the 19th and 20th centuries, Maxwell's unification of electromagnetism and Einstein's relativity reshaped our understanding of space, time, and gravity. Quantum mechanics revealed the strange behavior of particles at tiny scales, opening new mysteries about reality. The space age began with Sputnik in 1957, leading to human exploration of the moon and beyond. Today, understanding the four fundamental forces is key to grasping how the universe works, and the search for new forces continues to push the boundaries of science. There are four fundamental forces that govern the universe. Gravity. Gravity has infinite range and is always attractive. It controls the motion of planets, stars, galaxies, and even light by curving space-time, as explained by Einstein's general theory of relativity. Electromagnetism. Stronger than gravity, this force acts between charged particles. It governs electricity, magnetism, and light, explaining atomic and molecular behavior. Quantum electrodynamics describes this force. Weak nuclear force. This short-range force causes processes like beta decay in unstable atomic nuclei. It plays a key role in the nuclear reactions that power stars, enabling fusion. Strong nuclear force. The strongest force, but operating over tiny distances within atomic nuclei. It binds protons and neutrons together, overcoming electromagnetic repulsion, and is explained by quantum chromodynamics. Historically, scientists have expanded our understanding of these forces. Isaac Newton formulated laws of motion and universal gravitation, describing how masses attract each other and explaining planetary orbits. Galileo demonstrated that all objects fall at the same rate regardless of mass, reinforcing gravity's principles. James Clerk Maxwell unified electricity and magnetism into a single electromagnetic theory, revealing light as an electromagnetic wave and laying the foundation for modern technologies. Albert Einstein revolutionized our view of gravity with his theory of relativity, showing that gravity is the curvature of space-time caused by mass. His famous equation linked mass and energy, underpinning nuclear reactions. Quantum mechanics emerged in the 20th century through scientists like Niels Bohr and Werner Heisenberg, revealing that particles behave in ways that defy classical physics, such as superposition and entanglement. Enrico Fermi developed the theory of beta decay, explaining weak nuclear interactions, later refined by Steven Weinberg and Abdus Salam. Together, these forces shape the universe from the tiniest particles to vast cosmic structures, and understanding them continues to drive scientific discovery. In the 1970s, Abdus Salam developed the electroweak theory, unifying the weak nuclear force and electromagnetism into a single framework. This showed how these forces connect at high energy levels. The strong nuclear force, which binds protons and neutrons in atomic nuclei, was advanced by physicists like Hideki Yukawa, who proposed mesons as carriers of this force. This led to quantum chromodynamics, QCD, a theory refined by David Gross, Frank Wilczek, and David Politzer, earning them the Nobel Prize. Quantum mechanics revolutionized our understanding of forces, revealing that particles behave unpredictably at atomic and subatomic scales. Quantum electrodynamics, E, explains how light and matter interact, with particles exchanging virtual photons to mediate electromagnetic forces. This knowledge powers technologies like lasers and semiconductors. Quantum field theory describes nuclear forces via particle exchanges. Gluons for the strong force, and W and Z bosons for the weak force, helping unify our understanding of these interactions in extreme conditions like stars and particle accelerators. Efforts to understand gravity at the quantum level include theories like string theory and loop quantum gravity, aiming to combine quantum mechanics with general relativity, possibly unlocking mysteries of black holes and space-time fabric. Quantum mechanics introduced phenomena like entanglement and superposition, challenging classical ideas of locality. Entangled particles affect each other instantly, regardless of distance. Historically, Isaac Newton revolutionized physics in the 17th century by formulating the law of universal gravitation, showing that every mass attracts every other mass with the same force governing falling objects and planetary orbits. This unified earthly and celestial mechanics under one law. In the 20th century, Albert Einstein expanded this view with his general theory of relativity, describing gravity not as a force but as the curvature of space-time caused by mass. This led to concepts like time dilation, where time slows down near massive objects, a fact crucial for technologies like GPS satellites. Satellites like GPS must account for relativistic effects, such as time dilation caused by gravity, to provide accurate location data. This highlights how deeply intertwined our understanding of gravity is with theoretical frameworks used to study space and the universe. These frameworks help scientists interpret complex phenomena and guide research. A key example is Einstein's theory of general relativity, 1915, which describes gravity as the curvature of space-time caused by mass. This revolutionized physics by showing how massive objects like stars and planets warp space-time, producing the effects we perceive as gravity. In contrast, quantum mechanics deals with physics at very small scales, introducing concepts like wave-particle duality and uncertainty, which challenge classical physics. Together, General relativity and quantum mechanics form the foundation of modern physics, but remain incompatible in some ways. Scientists are still searching for a unified theory. Two leading candidates for such a unification are string theory. Proposes that the universe's fundamental building blocks are tiny vibrating strings rather than point particles. It predicts multiple dimensions beyond the familiar three of space and one of time. These extra dimensions might explain mysterious phenomena and potentially harbor additional fundamental forces beyond the four known ones. Gravity, electromagnetism, strong nuclear, and weak nuclear forces. Loop quantum gravity attempts to quantize space-time itself, suggesting that space is made of discrete units, like pixels on a screen. This approach aims to bridge the gap between general relativity and quantum mechanics, but remains a work in progress. The field of cosmology, which studies the universe's large-scale structure and evolution, relies heavily on these frameworks. For example, the cosmic microwave background radiation, the afterglow of the Big Bang, provides crucial data that theoretical models help explain. Theoretical frameworks also guide experimental science. Researchers formulate hypotheses based on existing theories and test them through observations or experiments. This iterative process, where theories are supported, refined, or replaced, drives progress in understanding the universe. Advances in technology, including artificial intelligence, continue to open new frontiers in research. While we currently recognize four fundamental forces, physicists have long speculated about additional forces hidden beneath the surface of our knowledge. Extra dimensions, as explored in Kaluza-Klein theory and string theory, could host forces that influence our universe in subtle ways. Modified gravity theories, such as MOND, modified Newtonian dynamics, try to explain galaxy rotation curves without invoking dark matter, suggesting gravity might behave differently under certain conditions. The search for a quantum theory of gravity opens possibilities for new forces emerging from quantum fluctuations. Experimental hints of a fifth force have appeared in particle physics, showing anomalous behavior that doesn't fit existing models. If confirmed, this force might operate under special conditions or scales, profoundly impacting physics and cosmology. Grand Unified Theories, GUTs, propose that at extremely high energies, the strong, weak, and electromagnetic forces unify into a single force, possibly with additional unknown interactions. String theory takes this further by positing that fundamental particles are vibrations of strings. Different vibrational modes correspond to different particles and forces, including the graviton, the hypothetical particle mediating gravity. Because string theory predicts multiple hidden dimensions, these could harbor forces beyond those in the standard model. The shape and size of these dimensions would influence how strings vibrate, thus determining the particles and forces we observe. Some versions, like M-theory, suggest our universe may be one among many, each with its own laws and forces. The discovery of new forces through string theory could help explain puzzles like dark matter and dark energy, which comprise most of the universe's mass energy, but remain mysterious. Physicists hope to detect evidence of these new forces in high-energy experiments, such as those at the Large Hadron Collider, LHC, where energies are sufficient to probe extra dimensions and their associated forces. As research continues, these theoretical frameworks guide our quest to understand the universe's deepest workings, bridging the smallest particles to the largest cosmic structures. Unification theories aim not only to understand the universe's fundamental structure, but also to identify potential new forces. These theories suggest that the four known fundamental forces, gravity, electromagnetism, weak nuclear, and strong nuclear, are interconnected and may be different aspects of a single force at very high energies. For example, in the early universe, extreme conditions likely unified these forces into one. Theoretical frameworks like string theory and grand unified theories, GUTS, explore this idea, with string theory proposing that fundamental particles are tiny vibrating strings, whose different modes create various particles and forces. This approach also seeks to reconcile gravity with quantum mechanics, a major challenge in physics. Understanding unification could reveal the nature of dark matter and dark energy, which make up most of the universe. It also sheds light on the early universe, such as the Big Bang and cosmic inflation, when all forces may have been unified before separating as the universe cooled. Beyond theory, unification has practical implications, potentially leading to advances in energy, materials science, and quantum computing. Experiments at particle accelerators, like the Large Hadron Collider, continue to test these ideas. Quantum gravity explores the attempt to merge general relativity, which describes gravity as space-time curvature, with quantum mechanics, which governs the microscopic world. This is difficult because gravity isn't a traditional force mediated by particles like photons or gluons, and space-time may have a discrete, foamy structure at quantum scales, contrasting with the smooth geometry of relativity. Challenges like the black hole information paradox, which questions whether information is lost inside black holes, highlight the limitations of current theories and the need for a quantum theory of gravity. The four fundamental forces govern particle interactions and the universe's structure. Gravity, the weakest but acts over long distances, shaping planets, stars, and galaxies. Electromagnetism, stronger than gravity, governs charged particles, electricity, magnetism, and light, essential for chemistry. Strong nuclear force, the strongest, binds protons and neutrons in atomic nuclei, mediated by gluons. Weak nuclear force, responsible for processes like beta decay involving neutrinos. The weak nuclear force is crucial for nuclear reactions that power stars, including our sun. It operates at very short distances, similar to the strong force, but is weaker than both the strong and electromagnetic forces. In particle physics, the relationship between fundamental forces and particles is described by models like the Standard Model. This model explains how forces interact with particles such as fermions, which make up matter, and bosons, which mediate forces. Each force is carried by specific particles. Photons carry the electromagnetic force, W and Z bosons mediate the weak force, and gluons carry the strong force. Understanding these interactions helps scientists explain phenomena ranging from subatomic particle behavior to the dynamics of galaxies. Research in particle physics also drives technological innovation, leading to advances in medical imaging, energy production, and materials science. Observational evidence from astronomy is key to understanding the universe. Data collected from telescopes, space probes, and other instruments allow scientists to study celestial objects and phenomena. One major source of evidence is the Hubble Space Telescope, which has captured stunning images of distant galaxies, nebulae, and other cosmic wonders. Light from these objects travels billions of years, providing insights into the age, composition, and expansion of the universe. Another important discovery is the cosmic microwave background radiation, CMB, the afterglow of the Big Bang, which fills the universe with faint radiation detectable from anywhere in space. The European Space Agency's Planck satellite has provided detailed measurements of this radiation, refining our understanding of cosmology. The detection of gravitational waves, ripples in space-time caused by massive events like merging black holes or neutron stars, has opened a new window into the universe. First observed in 2015 by the LIGO Observatory, these waves confirm predictions from Einstein's general relativity and allow scientists to study phenomena that were previously undetectable. Planetary exploration missions, such as NASA's Mars rovers, contribute valuable data on the Martian surface, atmosphere, and the potential for past life, including the search for water on other celestial bodies. The study of exoplanets, planets outside our solar system, has expanded rapidly due to missions like Kepler and TESS, which have discovered a wide variety of worlds, some in habitable zones where life could exist. Techniques like the transit method, where a planet dims its star's light as it passes in front, help detect these distant planets and enhance our understanding of planetary systems. Astronomical phenomena often hint at new forces or principles governing the universe. For example, many spiral galaxies, including the Milky Way, rotate faster than expected based on visible matter alone. This discrepancy suggests the presence of dark matter, an invisible substance exerting gravitational influence, though its nature remains a mystery. Gravitational wave studies may also reveal new aspects of gravity or unknown forces operating under extreme conditions. Finally, supernovae, explosive deaths of massive stars, are important for understanding fundamental forces. When a star exhausts its nuclear fuel and collapses, the light curves and behavior of the explosion provide clues about the forces involved and the evolution of the universe. The brightness changes over time in supernova explosions, known as their light curves, vary greatly depending on the underlying physics. Studying these light curves helps reveal new insights into stellar evolution, nuclear reactions, and the behavior of matter under extreme conditions, possibly pointing to forces beyond current knowledge. Cosmic rays, high-energy particles traveling through space, are another mystery that may hint at new forces. Originating from sources like supernovae or active galactic nuclei, some cosmic rays have energies far exceeding those produced on Earth. The mechanisms accelerating these particles might involve unknown forces, pushing physics beyond the standard model. The cosmic microwave background radiation, CMB, the faint glow left over from the Big Bang, provides clues about fundamental forces, early universe conditions, dark matter, and dark energy. Variations in temperature and density in the CMB help scientists understand the universe's origins and evolution. Dark matter and dark energy remain two of the greatest cosmic mysteries. Dark matter, making up about 27% of the universe's mass energy, cannot be seen directly since it does not emit, absorb, or reflect light. Its presence is inferred from gravitational effects, such as the unexpected rotation speeds of galaxies and gravitational lensing. It acts like an invisible glue, holding galaxies together. On the other hand, dark energy appears to drive the accelerated expansion of the universe. Unlike dark matter's attractive gravity, dark energy exerts a repulsive effect, pushing galaxies apart faster over time. Scientists speculate that dark matter and dark energy may be linked to unknown forces or particles. For example, WIMPs, weakly interacting massive particles, are leading dark matter candidates whose discovery could reveal new physics beyond the standard model. The nature of dark energy raises questions about gravity itself. Some theories propose modifications to gravity over large distances or entirely new forces at work. Some physicists explore the possibility of a fifth fundamental force beyond the four known ones: gravity, electromagnetism, strong nuclear, and weak nuclear forces that could explain dark matter and dark energy behaviors. The quest for a unified theory that merges quantum mechanics and general relativity may uncover connections between dark components and undiscovered forces. For example, string theory suggests extra dimensions beyond our familiar three spatial ones, which could hide new forces or particles influencing dark matter and dark energy. Recent observations of cosmic rays have revealed anomalies hinting at new physics. The Alpha Magnetic Spectrometer, AMS, on the International Space Station detected an unexpected excess of positrons, the antimatter counterparts of electrons, at high energies. This has sparked debates on whether these positrons arise from dark matter interactions or astrophysical sources like pulsars. Similarly, the Ice Cube Neutrino Observatory in Antarctica has observed high-energy neutrinos from beyond our galaxy, suggesting unknown astrophysical processes or forces at play. The Pamela satellite found discrepancies in cosmic ray proton and electron energy ratios, hinting at possible new forces affecting these particles or unknown phenomena influencing cosmic ray behavior. The discovery of the knee in the cosmic ray spectrum, a sharp drop in cosmic ray numbers at certain energies, has led to new theories about how cosmic rays propagate and the forces governing their behavior. Altogether, these cosmic mysteries offer tantalizing clues that could reshape our understanding of fundamental physics and the universe. Some researchers are investigating whether the knee in the cosmic ray spectrum, a sharp drop in cosmic ray numbers at certain energies, could signal previously unknown interactions. This might link cosmic rays to deeper areas of physics like quantum gravity or string theory. Although not yet fully understood, these cosmic ray anomalies open exciting possibilities in astrophysics by challenging existing theories. Gravitational waves and new forces. Gravitational waves, ripples in spacetime caused by the acceleration of massive objects such as merging black holes or neutron stars, play a fascinating role in the search for new fundamental forces. These cosmic events create disturbances that travel across the universe, stretching and squeezing space as they pass. Detectors like LIGO and Virgo are finely tuned to capture these subtle waves. By observing gravitational waves, scientists open a new window into the universe's fundamental workings, potentially revealing forces or interactions beyond current understanding. As researchers analyze gravitational wave data, they search for anomalies, any deviations from predictions made by Einstein's general relativity, which describes gravity as the curvature of spacetime caused by mass. Unexpected behaviors in gravitational waves could indicate the existence of new forces, particles, or extra dimensions not accounted for in current physics models, including the Standard Model, which describes electromagnetic, weak, and strong forces. For example, if gravitational waves from certain cosmic events show properties that differ from expectations, this might suggest the presence of extraspatial dimensions, new particles interacting in ways unknown to us, or modifications to gravity itself. These possibilities are explored in theories like string theory and loop quantum gravity, which propose gravity might not be the only force shaping the cosmos. Understanding gravitational waves may help confirm or rule out such theories, refining our comprehension of the universe. Gravitational waves as probes of the early universe. Gravitational waves can also provide insights into the very early universe, moments after the Big Bang, when different fundamental forces may have acted in ways no longer directly observable today. Detecting gravitational waves from this epoch could lead to breakthroughs in understanding how forces like electromagnetism and gravity emerged as the universe cooled and expanded, possibly revealing how these forces are interconnected. While the search for new forces via gravitational waves is still in its infancy, its implications are profound. As detection techniques improve and more data is collected, we may uncover entirely new aspects of fundamental physics, or even discover forces that govern cosmic behavior in ways previously unknown. Cosmic microwave background radiation, CMB. The cosmic microwave background, CMB, often abbreviated as CMB or sometimes Q in casual speech, is a faint glow permeating the entire sky and is a relic of the early universe. It is essentially the afterglow of the Big Bang, providing a snapshot of the universe approximately 380,000 years after its birth, when matter and radiation first decoupled. But in the end, matter becomes uncovered. The tiny temperature fluctuations and anisotropies, variations across the sky, observed in the CMB carry profound information about the universe's origins and the potential for new physics beyond current models. By studying these anisotropies in detail, scientists can test predictions from the inflationary model, a theory proposing the universe underwent a rapid, exponential expansion shortly after the Big Bang. The patterns we observe in the CMB either support or challenge these inflationary theories. For instance, certain non-Gaussian features in the CMB data could indicate interactions or phenomena that lie outside our current understanding, such as the presence of primordial gravitational waves, exotic quantum fields, or unknown particle interactions. Additionally, the polarization patterns of the CMBCA caused by scattering during the recombination era provide another pathway to explore new physics. Analysis of polarization helps us understand the effects of dark energy and dark matter on cosmic evolution. Unexpected deviations in polarization data might suggest new particles or interactions, potentially leading to groundbreaking advances in fundamental physics or beyond standard model physics. Moreover, the CMB serves as a powerful tool for exploring physics beyond the standard model, including supersymmetry, such theories involving extra dimensions, or other extensions that could explain dark matter, dark energy, and the unification of forces. New physics and the cosmic microwave background, CMB. Theories involving extra dimensions and supersymmetry often predict specific features in the early universe that could leave detectable imprints in the cosmic microwave background, CMB, radiation. For example, if particles predicted by supersymmetry were produced during the early universe, they might affect the temperature fluctuations we observe in the CMB today. By comparing precise CMB data with theoretical models, researchers can identify discrepancies that may hint at new particles or forces influencing cosmic evolution. This intersection of CMB studies and theoretical physics also relates to the search for cosmic inflation, the rapid expansion phase, thought to occur just after the Big Bang, and its underlying mechanisms. Experimental approaches in space exploration. Practical experimentation is vital for testing new scientific ideas and technologies before they are deployed on real space missions. Several innovative methods include CubeSats and small satellites, compact, lightweight, and cost-effective spacecraft that can be launched in groups to conduct experiments in microgravity. These experiments study biological processes, material science, and fluid behavior, providing data crucial for future long-duration missions to the Moon or Mars. In situ resource utilization. The practice of using local materials from celestial bodies to support human life and operations. For instance, scientists are investigating the extraction of water ice from permanently shadowed lunar craters. This water could supply drinking needs or be converted into rocket fuel, hydrogen and oxygen, reducing the need to carry everything from Earth. Astrobiology missions. Robotic missions like the Mars Perseverance rover search for signs of past microbial life on Mars. by analyzing soil and rock samples for organic compounds. This research enhances our understanding of Mars and informs the search for life on exoplanets with Earth-like conditions. 3D printing in space. Additive manufacturing technologies aboard the International Space Station allow astronauts to print tools, spare parts, and habitat components on demand. This reduces reliance on Earth-based supply missions and is essential for sustainable long-term space habitation. Advanced propulsion systems beyond traditional chemical rockets. Alternative propulsion methods like ion propulsion use electric fields to accelerate ions for more efficient long-distance travel, which is crucial for deep space missions. Searching for new fundamental forces. Scientists continually push the boundaries of understanding by exploring the possibility of new fundamental forces beyond the known four: gravity, electromagnetism, strong nuclear and weak nuclear forces. Cutting-edge experimental techniques include particle accelerators. Machines like the Large Hadron Collider, LHC, accelerate particles to near light speeds and smash them together, replicating conditions similar to the early universe. These collisions reveal new particles and interactions. For example, the LHC's discovery of the Higgs boson explained how particles acquire mass through the Higgs field. Accelerators continue to search for signs of supersymmetry, extra dimensions, or other unknown forces. Ultra-sensitive detectors. Utilizing superconducting materials and other advanced technologies, these detectors can measure extremely faint signals that might indicate new forces. They detect minute changes in energy or particle interactions, pushing the limits of current measurement capabilities. Tabletop experiments. Smaller-scale laboratory setups, like atomic interferometry, allow precision measurements of atomic behavior under different conditions. These experiments test for tiny deviations from the standard model predictions, potentially revealing new forces. Cosmic ray and astrophysical observations. High-energy particles from space provide natural laboratories for physics at energies unreachable on Earth. Studying their interactions helps identify possible new forces or particles influencing the universe. Quantum mechanics and entanglement. Research into quantum phenomena, such as entanglement, seeks anomalies that could suggest new interactions or fundamental forces connecting distant particles in unexpected ways. The importance of global collaboration. Progress in understanding fundamental forces relies heavily on collaboration among global research institutions. Sharing data, resources, and expertise enables breakthroughs that individual labs might not achieve alone. Diverse scientific perspectives foster innovative approaches to complex questions about the universe's understanding, the Higgs boson, and particle accelerators. The discovery of the Higgs boson has deepened our understanding of the standard model of particle physics. This particle explains how other particles acquire mass through the Higgs field. A fundamental insight into the forces that govern our universe, including the strong and weak nuclear forces responsible for atomic interactions. Particle accelerators play a critical role in exploring phenomena beyond just the Higgs boson. They allow scientists to study antimatter, the mirror image of ordinary matter, which is essential in understanding the asymmetry between matter and antimatter in the cosmos. By observing how antimatter behaves under various conditions, researchers gain insights into fundamental forces such as gravity, electromagnetism, and the nuclear forces. Probing cosmic rays and extreme astrophysical phenomena. Particle accelerators also contribute to the study of cosmic rays, high-energy particles traveling through space that strike the Earth's atmosphere. By simulating these interactions, scientists investigate how cosmic rays affect matter and explore astrophysical phenomena like supernovae and black holes. This research sheds light on the complex interplay of gravity, electromagnetic forces, and nuclear forces in extreme environments. Beyond subatomic particles, accelerators can simulate conditions found inside stars and other celestial bodies, providing insights into stellar formation, energy production, and the fundamental forces active in these environments. Unlocking new forces. The Large Hadron Collider, LHC, operated by the European Organization for Nuclear Research, CEN, is the world's largest and most powerful particle accelerator. Situated underground, it collides particles at energies up to 7 tera-electron volts, VAB, ZE, recreating conditions similar to moments after the Big Bang. The LHC has been pivotal in exploring the nature of the Higgs boson and searching for new physics beyond the Standard Model. For example, it investigates the properties of the Higgs boson to understand if it hints at unknown forces or interactions. It searches for supersymmetry, SUY, a theory proposing that every known particle has a heavier superpartner. Detecting SUSY particles could provide critical clues about dark matter, which makes up about 27% of the universe, but remains invisible and undetected. The LHC also explores the possibility of extra dimensions, predicted by some theoretical models. These could open pathways to new forces that extend beyond our familiar three-dimensional universe. By smashing protons together near the speed of light, the LHC creates rare and extreme conditions where such new phenomena might appear. Physicists analyze vast amounts of collision data using advanced algorithms to detect subtle signals that could indicate new physics or forces. Collaborative science and satellite experiments. Thousands of scientists worldwide collaborate at the LHC, sharing knowledge and expertise, which accelerates progress in fundamental physics. Satellite experiments complement ground-based accelerators by collecting data from space, an environment inaccessible to Earth-based observatories. Satellites can observe cosmic phenomena with high precision, capturing signals and particles that might reveal unknown forces. Instance, the Gaia mission by the European Space Agency is mapping the Milky Way with unprecedented accuracy. Its data provides new insights into the distribution of dark matter, which cannot be observed directly but influences the motion of stars and galaxies. Satellites equipped with advanced sensors monitor cosmic rays and their interactions with Earth's atmosphere. Studying these can reveal unexpected patterns or behaviors that hint at new fundamental forces. These space-based observations are crucial for understanding gravity and electromagnetism in environments unreachable from Earth. Future frontiers, gravitational waves, and beyond. New experimental projects like the Laser Interferometer Space Antenna, LISA, aim to detect gravitational waves directly from space. This will open a novel window into astrophysical events and potentially reveal interactions or forces that challenge our current understanding of physics. Exploring new forces in space and time. Gravitational waves, ripples in space-time caused by massive cosmic events like black hole mergers, offer powerful insights into gravity and the nature of space-time. Detectors like LISA could confirm Einstein's theories and uncover new aspects of gravitational interactions. And if only .B could set the ripples off too. Panic is not a help. The answer is almost always. Satellite missions, such as Planck, study the cosmic microwave background to understand the universe's early evolution and the forces that shaped it. As satellite technology advances, innovations like quantum sensors may help detect entirely new forces in the universe. To capture these elusive signals, scientists use advanced detectors. Particle detectors, like ATLAS and CMS at the LHC, track particles from high-energy collisions, revealing force interactions. Neutrino detectors, like IceCube, observe faint signals from elusive particles, potentially pointing to supersymmetry or extra dimensions. Gravitational wave detectors, e.g., LIGO and Virgo, sense tiny space-time distortions from cosmic collisions. Electromagnetic detectors, e.g., CCDs, measure light and radiation from distant stars and supernovae, offering clues about dark energy and gravity. Theoretical concepts, such as dark matter, dark energy, and modified gravity, challenge existing physics. Quantum mechanics raises profound questions, like the black hole information paradox, and the multiverse theory suggests our universe might be just one of many. These ideas push the boundaries of science, forcing us to rethink time, space, and reality itself. The implications of discovering new forces and extraterrestrial life. Extraterrestrial life. The discovery of alien life, microbial or intelligent, would have massive implications. Beyond biology, it would force us to re-examine our place in the universe. Philosophical and ethical questions about interacting with other life forms. Our responsibilities in communication, especially regarding SETI, Search for Extraterrestrial Intelligence. Cosmic inflation and new forces. The theory of cosmic inflation, rapid expansion just after the Big Bang, raises questions about the uniformity of the universe and its hidden structures. This could lead to the discovery of a new fundamental force beyond the four known ones: gravity, electromagnetism, strong and weak nuclear forces. A major revision of the standard model of particle physics, which currently struggles to integrate gravity. Uncovering the fifth force. A fifth force could explain dark matter and dark energy, which make up about 95% of the universe, yet remain mysterious. Offer new understanding of galaxy formation, gravitational effects, and cosmic expansion. Possibly relate to cosmic inflation and the conditions right after the Big Bang. Technological and scientific advances. Historically, understanding fundamental forces has led to major technologies, from semiconductors to MRI machines. A new force could revolutionize energy production, medical technology, communication systems, philosophical and cosmic implications. A new force could challenge our understanding of reality and dimensions. The constants of physics, like the speed of light or gravitational strength. How matter and energy behave across the cosmos. Cosmic and stellar effects. A new long-range force could alter how galaxies interact, potentially reshaping large-scale structures. At the quantum level, it might affect stellar fusion, changing star brightness, lifespan, and element formation. It may even lead to new types of black holes or celestial objects we've never seen. Dark matter and dark energy. A deeper understanding of a new force could help explain how dark matter influences galaxy behavior, how dark energy drives the accelerated expansion of the universe. The discovery of a new fundamental force would not just alter our scientific understanding, it would profoundly reshape the way we view the universe, reality, and even ourselves. At the core of modern physics lies the Standard Model, a well-established framework that describes fundamental particles and three of the four known forces: electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity, however, remains dimensions outside this model, explained instead by Einstein's general theory of relativity. Introducing a new force would necessitate a re-evaluation of this entire framework. It could mean that there are particles and interactions yet to be discovered, hidden aspects of reality that elude even our most powerful instruments. Much like the discovery of the Higgs boson validated our understanding of how particles acquire mass, a new force might confirm entirely new mechanisms that govern the universe. Such a revelation could point to extra dimensions or an extended theoretical landscape, as suggested by string theory and other attempts to unify gravity with quantum mechanics. These ideas could help solve some of the biggest mysteries in physics today, such as the true nature of dark matter and dark energy, two components that together make up about 95% of the cosmos, yet remained largely unexplained. Dark energy, in particular, is believed to be responsible for the accelerated expansion of the universe. If a new force is connected to it, it could challenge fundamental principles such as the conservation of energy. The first law of thermodynamics, that energy cannot be created or destroyed, might need to be revisited if energy can be converted in ways we have yet to comprehend. Similarly, the second law, which states that entropy always increases in an isolated system, might behave differently across vast cosmological scales, or in regions influenced by dark energy, or within the multiverse. The behavior of black holes already presents challenges to our classical understanding of thermodynamics. Phenomena like Hawking radiation, which suggests that black holes can lose mass and energy, raise complex questions about how energy and information are conserved. The presence of a new force in such extreme environments could force a complete rethink of how these cosmic giants function. This potential new force could also transform our understanding of cosmic structure. It might explain how galaxies form, interact, or cluster in ways that gravity alone cannot fully describe. If it operates at very large distances, it could modify the gravitational attraction between galaxies, possibly introducing a form of repulsion or new patterns of movement we have yet to observe. Such a force might help explain the filamentary web-like structure of the universe, or reveal even more intricate arrangements of matter. At the quantum level, a new force could influence how particles behave inside stars, changing the processes of nuclear fusion that power them. This could lead to stars with different lifespans, energy outputs, or element production cycles, which, in turn, would affect the cosmic abundance of vital elements like carbon and oxygen, elements essential to life. Moreover, the implications are not confined to scientific theory. Discovering a new force could lead to technological breakthroughs far beyond our current imagination. Just as understanding electromagnetism gave rise to radio, electricity, and the digital age, a new force might inspire innovations in medicine, energy, and communication. It could even open the door to advanced propulsion systems or new ways of manipulating matter and energy. Philosophically, the discovery of a new force would prompt humanity to question the very nature of reality. Are there hidden dimensions influencing our world? Is our understanding of the universe only a fraction of the full picture? These questions touch not only on science, but also on metaphysics, theology, and the boundaries of human knowledge. In essence, the universe might be governed by rules and interactions that we are only beginning to glimpse. The discovery of a new fundamental force would not just be a scientific achievement, it would be a moment of existential awakening, a turning point in our quest to understand the cosmos and our place within it. If new forces exist in the universe, their discovery would have profound implications for our understanding of the laws of physics. It would force us to rethink the foundational principles that govern reality as we know it. What we consider scientific truth is built upon established theories. But if these theories can be overturned or deeply revised, then truth itself may be more flexible than we assumed. This leads to a deeper reflection on the nature of scientific progress. Is science a steady march toward an ultimate truth, or is it a series of approximations, continually updated or even replaced as we uncover more of nature's hidden layers? If a new force were to interact with matter in a way we don't yet understand, this might call into question our basic assumptions about causality and the predictability of the universe. Such forces might suggest a universe far more complex and interconnected than we ever imagined. They may prompt us to reconsider our place within it, not as passive observers, but as beings with limited perception trying to map a reality that might go well beyond our sensory or technological reach. Philosophically, this touches on age-old debates. Are there limits to human understanding? Are there aspects of reality that are fundamentally unknowable? These questions echo the divide between scientific realism and anti-realism. Realism holds that an objective universe exists independently of our observations. Anti-realism suggests that what we know is always filtered through perception, meaning our grasp of reality could be inherently constrained. If new forces operate beyond the range of direct observation, we face a challenge. How do we continue to use empirical methods when the very things we seek to understand may be invisible to current instruments? This could lead to a shift in how we validate scientific knowledge, perhaps embracing more abstract forms of inference, or entirely new methodologies. The implications extend beyond science into ethics and existentialism. If humanity gains the ability to harness such forces, to manipulate matter or energy in ways we barely comprehend, we must also consider the moral responsibility that comes with such power. Are we prepared, ethically, to engage with forces that could reshape life, energy, and even the cosmos? Or would our historical tendencies toward exploitation re-emerge, possibly with even greater consequences? This raises important questions about the relationship between knowledge and power. Is the pursuit of knowledge justified for its own sake, even if it might lead to dangerous or uncontrollable capabilities? These concerns highlight the importance of coupling scientific advancement with moral and philosophical reflection. Beyond ethics, the very nature of existence could be called into question. Are new forces simply extensions of what we already know? Or do they point to an entirely different layer of reality, one that alters our understanding of space, time, and matter? When we contemplate the universe, it's easy to become overwhelmed by its vast scale. The observable universe spans roughly 93 billion light-years in diameter, a scale so immense it defies intuitive understanding. To offer some perspective, 1 light-year equals approximately 5.88 trillion miles. Even imagining these distances is a cognitive challenge, but doing so is essential for grasping our place in the cosmos. Our home galaxy, the Milky Way, contains an estimated 100 to 400 billion stars and stretches across about 100,000 light-years. Traveling at the speed of light, it would take us 100,000 years to cross it. Yet the Milky Way is just one of billions of galaxies in the universe. It is part of a group of galaxies known as the Local Group, which itself belongs to the much larger Laniakea supercluster, a cosmic structure spanning about 520 million light-years and containing over 100,000 galaxies. This interconnectedness on a cosmic scale is governed by fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. Gravity shapes the motion of planets, stars, and galaxies, while electromagnetism enables the formation of atoms and molecules. The strong force binds atomic nuclei together, and the weak force governs certain types of radioactive decay. Yet even with this knowledge, much of the universe remains a mystery. Dark matter and dark energy, for example, make up around 95% of the universe. Dark matter affects how galaxies rotate and cluster together, while dark energy drives the accelerating expansion of the universe. These phenomena do not fit neatly into the standard model of particle physics, and their exact nature remains elusive. The discovery of new forces could radically transform our understanding of these cosmic components. New interactions might influence the behavior of dark matter, altering how galaxies form and evolve. They could also shift the balance between visible matter and dark matter, changing how galaxies cluster and move across cosmic time. On a grander scale, if these forces operate over vast distances, they might affect the dynamics of galaxy clusters, immense collections of galaxies bound together by gravity. Interactions between galaxies might change, potentially leading to new patterns of galaxy merging or dispersal. Cosmic structures could become more intricate, shaped by forces we have yet to include in our models. Even the large-scale structure of the universe, the cosmic web of filaments connecting galaxies, could be influenced. These filaments guide the flow of matter across the cosmos. If new forces act on these filaments, they might enhance or suppress the movement of gas and dark matter, leading to bursts of star formation in some regions and suppression in others. The cosmic landscape could become more dynamic and variable than we ever anticipated. Furthermore, the introduction of new forces would impact our understanding of cosmology itself. Current models of the universe's evolution depend on a delicate interplay between gravity and dark energy. If new forces are added to the equation, they could change how we think about cosmic expansion, structure formation, and even the ultimate fate of the universe. In the end, the discovery of new forces would not merely advance physics. It would challenge the boundaries of human knowledge, ethics, and existence. It would push us to confront the limits of perception, the responsibilities of power, and the true complexity of the universe we inhabit. It could trigger a new scientific revolution, one not only of equations and experiments, but of perspective, meaning, and purpose. The discovery of new forces could transform our understanding of the universe, forcing us to reconsider fundamental laws of physics. If such forces exist, they may reveal that science is not a linear path to truth, but a series of evolving approximations. This raises questions about causality, the limits of human understanding, and the nature of scientific realism. Are there aspects of reality we can never fully grasp? New forces might act in ways we can't yet observe, challenging our current methods of empirical investigation. Ethically, gaining control over unknown forces raises concerns about human readiness to use such power responsibly. This ties into a broader philosophical debate about whether the pursuit of knowledge should have limits. Cosmologically, these forces could reshape our view of galaxy formation, dark matter, and the large-scale structure of the universe. They may explain mysteries like the accelerated expansion of the cosmos or dark matter's influence on galactic motion. Theoretical concepts like a fifth fundamental force or modifications to gravity could dramatically alter how we understand space, time, and evolution of galaxies. Even black holes and neutron stars, regions governed by extreme physics, might behave differently under new forces. This could offer answers to long-standing puzzles like the black hole information paradox, or introduce new observational methods using high-energy radiation or gravitational waves. Ultimately, the discovery of new forces might lead to a paradigm shift in physics, unlocking deeper insights into the fabric of reality and the unseen complexity of the cosmos. In extreme environments like neutron stars, the behavior of fundamental forces becomes especially intriguing. Neutron stars, the remnants of massive supernovae, are incredibly dense and exert immense gravitational pull. This warps space-time and affects surrounding physics. The balance between gravity and nuclear forces keeps these stars stable, sometimes even preventing collapse into black holes. Near their surfaces, fascinating phenomena like neutron star winds occur, streams of charged particles driven by rapid rotation and intense magnetic fields. These magnetic fields can be billions of times stronger than Earth's and accelerate particles to near light speed, emitting high-energy X. To understand how forces behaved at the beginning of the universe, scientists turned to theoretical physics. During the Big Bang, all fundamental forces, gravity, electromagnetism, and nuclear forces, are believed to have been unified. This idea is central to the grand unification theory. Physicists use models from general relativity and quantum mechanics to simulate the universe's first moments. But merging these theories into a single model, often called quantum gravity, remains a major challenge. String theory is one possible solution, proposing that particles are tiny vibrating strings that could unify all forces. Experiments like those at the Large Hadron Collider recreate high-energy conditions similar to the Big Bang, offering insight into how particles and forces interacted in the early universe. Research into the Higgs field also reveals how particles gain mass, shaping how forces behave. Beyond the scientific realm, space exploration has had profound technological and societal impacts. Satellite technology now enables global communication, GPS navigation, and real-time weather forecasting. It also helps monitor climate change, deforestation, and disasters, informing global policy and action. Materials developed for space missions, lightweight, durable, heat-resistant, have found their way into sportswear, medical tools, and consumer goods. Technologies pioneered by NASA, like water purification and advanced robotics, benefit life on Earth in healthcare, industry, and remote areas. International cooperation in space, like the ISS, fosters peace and inspires young minds to pursue careers in science, engineering, and technology. This collective curiosity pushes humanity forward, reminding us of our shared existence and the need to protect our planet. Finally, discovering a new fundamental force could lead to revolutionary technology. For instance, it could stabilize quantum bits in quantum computers, making them vastly more powerful. Or it could lead to gravity-based propulsion systems, possibly enabling faster-than-light travel. In every way, from scientific understanding to everyday life, exploring the fundamental forces of the universe continues to shape our future in profound and unexpected ways. The transformative potential of discovering new fundamental forces. Imagine a future where traveling to Mars takes days instead of months. This could become a reality if we discover a new fundamental force capable of altering gravity or propulsion systems. Such a breakthrough would revolutionize space exploration, enabling efficient transportation of people and resources across the solar system and opening the door to colonizing other planets. But the impact of a new force wouldn't stop there. Energy, unlimited potential. If a new force allowed us to harness energy from the vacuum of space, we could unlock a virtually unlimited energy source. Devices could draw power from the very fabric of the universe, solving Earth's energy crisis and powering future off-world colonies and space missions. Materials. Matter on demand. Manipulating particles at the most fundamental level could usher in a new era in material science. Imagine substances that change their strength or weight on command. Perfect for aerospace, construction, even clothing. These materials would enhance safety, durability, and efficiency across countless industries. Medicine, healing from within. In medicine, a newly discovered force might let us control biological processes at the cellular or atomic level. We could target diseases more precisely, regenerate organs, or even reverse cellular aging. This would drastically improve human health and longevity. Communication, the quantum leap. New fundamental forces could transform communications. Quantum-level manipulation could lead to ultra-secure communication systems and extremely fast quantum networks. This would revolutionize global connectivity, cybersecurity, and information sharing. Future space missions and technologies. Looking ahead, several forces, both physical and societal, are reshaping the future of space exploration. Propulsion systems. Ion propulsion, already used on NASA's Dawn spacecraft, is being refined. It allows for more efficient, faster space travel. A new force could take this even further, perhaps enabling faster-than-light journeys. Material science. Innovations like graphene and ultra-durable composites are making spacecraft lighter and stronger, reducing risks from micrometeoroids and space radiation. Artificial intelligence, AI systems, can analyze data and make real-time decisions in deep space, essential for autonomous exploration far from Earth. Global collaboration. Private companies and international space agencies are increasingly working together, making missions more cost-effective and widespread. SpaceX, Blue Origin, and others are paving the way for a new era of commercial spaceflight. Resource discovery, moons like Europa and Enceladus, as well as asteroids, may contain water and rare metals. These resources could sustain future colonies and create new industries in space. Life support innovations. Long-duration missions require closed-loop systems. Bioregenerative methods, like growing food in space and recycling waste, are advancing quickly and are vital for missions to Mars and beyond. Beyond the known. Searching for new forces. Current physics recognizes 4 fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. But researchers continue to explore the possibility of a 5th force, or new aspects of the existing ones. Discovering such a force could revolutionize renewable energy. New energy systems that are clean, limitless, and efficient. By Atta Electronics. High-temperature superconductors enabling lossless power transmission. Propulsion, faster interplanetary travel, even possible interstellar exploration. Quantum technology, breakthroughs in computing and communication beyond our current capabilities. Engaging the public in physics. To ensure continued progress and support, public interest in physics must be cultivated. Here's how. Science communication. Break down complex ideas into engaging, relatable content through lectures, podcasts, videos, and infographics. Pop culture integration. Films, books, and series can portray physics in a captivating light, inspiring young minds. Hands-on learning, science fairs, summer programs, and school partnerships give students early exposure to real research. Social media engagement. Platforms like TikTok and YouTube can reach a wide audience with short, digestible content and live Q&As. Public exhibits and festivals. These events create interactive opportunities for people to meet scientists and explore cutting-edge research. Storytelling. Blogs and vlogs that tell the human stories behind the science make the field more approachable and relatable. A new era of discovery. The search for new fundamental forces isn't just theoretical. It's the foundation for a future filled with limitless energy, revolutionary technologies, advanced medicine, and deep space travel. As we push the boundaries of science, we are not just uncovering the secrets of the universe, we're building the tools to shape humanity's future among the stars. The universe is vast, mysterious, and full of questions that fascinate scientists and enthusiasts alike. One of the most exciting areas in modern physics is the search for new fundamental forces beyond the four we know: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. For decades, researchers have wondered if there could be additional forces that operate on scales we don't yet understand. Some scientists suggest a fifth force might exist, possibly connected to dark matter or dark energy, which could explain the universe's accelerating expansion. To find these forces, scientists study high-energy particles and cosmic phenomena, hoping to unlock new secrets of reality. Scientists study particle collisions at places like the Large Hadron Collider, where particles smash together at high speeds, recreating conditions just after the Big Bang. These experiments may reveal new particles or forces beyond the known four fundamental forces: gravity, electromagnetism, strong nuclear, and weak nuclear forces. Exploding in new forces could help explain mysterious gravitational effects seen in galaxy rotations, or even unify general relativity with quantum mechanics, transforming our understanding of the universe. Symmetry in nature also plays a key role in these forces, and exploring it might unlock new interactions. String theory suggests extra dimensions beyond our familiar three, which could harbor unique forces affecting the cosmos. Some theories even propose that time itself may be influenced by unknown forces, challenging our ideas of reality and causality. Throughout history, humanity's curiosity about the cosmos has driven scientific progress, from ancient civilizations using stars for navigation to the Greek philosophers proposing early models of the universe. The Middle Ages preserved and expanded this knowledge, leading to the Renaissance. The heliocentric model, introduced by Copernicus, refined by Kepler's planetary laws and Newton's gravity, revolutionized astronomy. The invention of the telescope allowed direct observations, supporting these ideas. In the 19th and 20th centuries, Maxwell's unification of electromagnetism and Einstein's relativity reshaped our understanding of space, time, and gravity. Quantum mechanics revealed the strange behavior of particles at tiny scales, opening new mysteries about reality. The space age began with Sputnik in 1957, leading to human exploration of the moon and beyond. Today, understanding the four fundamental forces is key to grasping how the universe works, and the search for new forces continues to push the boundaries of science. There are four fundamental forces that govern the universe. Gravity. Gravity has infinite range and is always attractive. It controls the motion of planets, stars, galaxies, and even light by curving space-time, as explained by Einstein's general theory of relativity. Electromagnetism. Stronger than gravity, this force acts between charged particles. It governs electricity, magnetism, and light, explaining atomic and molecular behavior. Quantum electrodynamics describes this force. Weak nuclear force. This short-range force causes processes like beta decay in unstable atomic nuclei. It plays a key role in the nuclear reactions that power stars, enabling fusion. Strong nuclear force. The strongest force, but operating over tiny distances within atomic nuclei. It binds protons and neutrons together, overcoming electromagnetic repulsion, and is explained by quantum chromodynamics. Historically, scientists have expanded our understanding of these forces. Isaac Newton formulated laws of motion and universal gravitation, describing how masses attract each other and explaining planetary orbits. Galileo demonstrated that all objects fall at the same rate regardless of mass, reinforcing gravity's principles. James Clerk Maxwell unified electricity and magnetism into a single electromagnetic theory, revealing light as an electromagnetic wave and laying the foundation for modern technologies. Albert Einstein revolutionized our view of gravity with his theory of relativity, showing that gravity is the curvature of space-time caused by mass. His famous equation linked mass and energy, underpinning nuclear reactions. Quantum mechanics emerged in the 20th century through scientists like Niels Bohr and Werner Heisenberg, revealing that particles behave in ways that defy classical physics, such as superposition and entanglement. Enrico Fermi developed the theory of beta decay, explaining weak nuclear interactions, later refined by Steven Weinberg and Abdus Salam. Together, these forces shape the universe from the tiniest particles to vast cosmic structures, and understanding them continues to drive scientific discovery. In the 1970s, Abdus Salam developed the electroweak theory, unifying the weak nuclear force and electromagnetism into a single framework. This showed how these forces connect at high energy levels. The strong nuclear force, which binds protons and neutrons in atomic nuclei, was advanced by physicists like Hideki Yukawa, who proposed mesons as carriers of this force. This led to quantum chromodynamics, QCD, a theory refined by David Gross, Frank Wilczek, and David Politzer, earning them the Nobel Prize. Quantum mechanics revolutionized our understanding of forces, revealing that particles behave unpredictably at atomic and subatomic scales. Quantum electrodynamics, QED, explains how light and matter interact, with particles exchanging virtual photons to mediate electromagnetic forces. This knowledge powers technologies like lasers and semiconductors. Quantum field theory describes nuclear forces via particle exchanges, gluons for the strong force and W and Z bosons for the weak force, helping unify our understanding of these interactions in extreme conditions like stars and particle accelerators.